Welcome to Podcast Learn and Fun. Let's start today's journey of learning. Today we're going to explore something you encounter constantly without even realizing it. Hydrogen bonds. They're the forces that hold our DNA together, give water its unique properties, and even help enzymes speed up those essential chemical reactions happening inside you right now.
It's true, hydrogen bonds are everywhere, but here's the catch. They're not your typical chemical bond. They operate in a realm where the rules of quantum mechanics hold sway, a world where things get a little fuzzy, and our everyday intuition needs a serious upgrade.
Quantum mechanics, huh? That sounds intimidating.
Yeah.
What's so different about this quantum world that makes hydrogen bonds so special?
Well, in the quantum world, particles like protons and electrons aren't just tiny balls zipping around. Instead of fixed locations, they're described by something called wavefunctions, which are like fuzzy clouds of probability indicating where a particle is most likely to be found.
So instead of those neat little diagrams we see in textbooks with electrons orbiting the nucleus like planets around the sun, it's more like a blurry, constantly shifting dance.
That's a great way to visualize it. And when a hydrogen atom with its single proton and electron gets close to another atom with a lone pair of electrons, things get really interesting. The proton's wave function can actually overlap with the wave function of those lone pair electrons.
Okay, so we've got these overlapping blurry clouds.
Yeah.
How does that actually translate into a bond? It's like they're reaching out to each other with ghostly hands.
Well, that overlap lowers the energy of the system. And you know what they say? Nature loves to be in a low energy state. It's all about finding that sweet spot where the system is most stable, like rolling downhill until you reach the bottom.
So the hydrogen bomb is all about finding that comfy, low-energy spot where those wave functions can hang out. But I have to admit, this whole wave function thing still feels a bit abstract. How does this quantum fuzziness explain why hydrogen bonds are so important in the real world?
Think about water. It's a simple molecule, just two hydrogen atoms bonded to an oxygen atom. But its properties are extraordinary. Water has a surprisingly high boiling point for such a small molecule. It's a fantastic solvent, dissolving all sorts of substances. It has high surface tension, allowing insects to walk on its surface. And all of these properties are thanks to hydrogen bonds.
So these fuzzy wave functions overlapping, creating these low-energy attractions, that's what gives water its superpower. It's incredible to think that something so small and strange is responsible for something so essential to life.
Exactly. And remember, we're not just talking about water. Hydrogen bonds are at play in countless biological processes, from the structure of DNA, our genetic blueprint, to the intricate folding of proteins, the workhorses of our cells. It's a quantum dance happening everywhere around us.
Wow, that's truly mind-blowing. So next time I see the glass of water, I'll be thinking about those tiny protons and electrons doing their quantum dance, all thanks to these bizarre yet powerful hydrogen bonds. But I have to ask, is there anything even weirder going on down there at the quantum level?
Oh, absolutely. Things get even stranger when we start talking about quantum tunneling. Imagine a proton facing an energy barrier like a wall. In our everyday world, it would need enough energy to climb over. But in the quantum world, it has a chance to just tunnel right through.
Wait, what? Tunneling through walls? That sounds like something straight out of a science fiction movie. How can something like that even be possible?
It's one of the most mind-bending aspects of quantum mechanics because a particle's position is spread out in this fuzzy wave function. A part of that wave function can actually extend beyond the barrier. It's as if the proton has a ghostly hand reaching through the wall, and there's a chance it can suddenly pop up on the other side.
So these protons are like tiny escape artists defying the laws of physics as we know them. But how often does this tunneling actually happen in hydrogen bonds? Is it a rare event, or is it going on all the time?
It happens all the time. In fact, it's one of the reasons hydrogen bonds are so flexible and dynamic. The proton isn't stuck in one place. It's constantly exploring different possibilities thanks to this quantum tunneling.
This is blowing my mind wide open. So these protons are zipping around, tunneling through barriers, all while their wave functions are overlapping and creating these strange attractions. It's like a chaotic yet perfectly choreographed dance at the tiniest level imaginable.
You got it. And this quantum dance has huge implications for things like how enzymes work and even how water behaves. It's a whole new way of looking at the world around us.
Okay, I'm officially hooked on this quantum adventure. I never realized how much was going on at such a small scale. So the next time I have a glass of water, I'll be thinking about all the tiny protons tunneling and wave functions overlapping. It's incredible to think that something so weird and wonderful is happening right under our noses.
Exactly. And remember, these quantum effects aren't just happening in water. They're at play in DNA, proteins, and countless other molecules essential for life. It truly is a quantum dance happening everywhere.
This has been an amazing journey so far, and I'm eager to learn even more about the strange and wonderful world of hydrogen bonds. But before we move on, I want to hear from you, our listeners. What are your initial thoughts? Are you as fascinated by this quantum dance as we are?
We'd love to hear your questions and insights. Feel free to share them in the comments below.
Absolutely. We always appreciate hearing from our audience. And who knows, maybe your questions will spark new avenues of exploration and discovery.
The world of science is vast and ever-evolving, and there's always something new to learn and explore. So keep those curious minds engaged, and join us next time as we continue our deep dive into the fascinating world of hydrogen bonds. Let's delve a bit deeper into this idea of proton tunneling and how it impacts the world around us. Remember, this quantum phenomenon allows a proton to essentially bypass an energy barrier, even if it seemingly lacks the energy to do so.
It's like walking through walls. I'm still wrapping my head around that concept.
It's definitely one of the weirder aspects of quantum mechanics. But think of it this way in the quantum world. A particle's position isn't fixed. It exists as this fuzzy cloud of probability described by its wave function.
So instead of a tiny ball in a specific spot, it's more like a smear of possibilities.
Exactly. And because it's spread out like that, a portion of the wave function can extend beyond the energy barrier. It's almost as if a part of the proton always existed on the other side, and tunneling just makes that connection.
So it's not really teleporting, it's more like revealing a hidden path that was always there.
That's a fantastic way to think about it. And this ability of protons to tunnel has a huge impact on how hydrogen bonds behave, particularly in biological systems.
I bet. Considering how vital hydrogen bonds are to life, I can only imagine how crucial this tunneling must be.
You're absolutely right. Let's take enzymes, for example. These are proteins that act as catalysts, speeding up crucial chemical reactions within living organisms. Many enzymes rely on proton transfer as part of their function, and this transfer is often facilitated by quantum tunneling.
So without tunneling, these reactions wouldn't happen efficiently enough to sustain life.
It's remarkable, isn't it? Something so fundamental to life relies on this seemingly bizarre quantum phenomenon.
It really underscores how deeply intertwined quantum mechanics is with the everyday world around us.
Absolutely. Quantum mechanics is often portrayed as this esoteric, abstract theory, but it's the very foundation of everything around us, even the processes that keep us alive.
Okay, so we've explored how proton tunneling influences hydrogen bonds. But what about the other fundamental particle at play here, the electron? Does it exhibit tunneling behavior as well?
Of course. Electrons are also quantum particles bound by the same peculiar rules of the subatomic realm.
So electrons can be wall walkers too. Do they contribute to the hydrogen bonding dance as well?
While electron tunneling doesn't directly participate in the formation of hydrogen bonds themselves, it plays a crucial role in numerous other processes, many of which underpin vital technologies. Think of transistors, the building blocks of modern electronics, or scanning tunneling microscopes, which allow us to visualize the world at an atomic level.
Wow, so quantum mechanics isn't just essential for understanding life. It's the driving force behind many technological marvels as well.
Precisely. Its influence is truly pervasive, shaping both the natural and technological landscapes we inhabit.
This is truly eye-opening. I'm beginning to perceive the quantum world in a completely new light. It's not some distant abstract realm, but an integral part of our reality woven into the very fabric of existence.
That's the beauty of scientific inquiry, constantly challenging our perceptions and expanding our understanding of the universe. Now, shifting gears a bit, let's revisit the concept of zero-point energy, which we touched upon earlier. Recall that it plays a significant role in shaping the dynamics of hydrogen bonds.
Right, zero-point energy, that minimum energy a system can possess even at absolute zero temperature.
Yeah.
But I thought at absolute zero, all motion ceases.
That's what classical physics would suggest, but as we've seen, the quantum world dances to a different tune. One of the fundamental principles of quantum mechanics is the Heisenberg uncertainty principle, which states that we can't simultaneously know both the precise position and momentum of a particle.
So even at absolute zero, there's still an inherent fuzziness to the particle's motion, preventing it from completely settling down.
Exactly. This residual motion, known as zero-point motion, contributes to the system's overall energy, even in its supposedly frozen state.
So even in their lowest energy configuration, hydrogen bonds are still subtly jiggling about thanks to the zero-point energy.
Precisely. And this persistent jiggling has a tangible effect on the properties of these bonds. For instance, it can slightly weaken the bond and impart a greater degree of flexibility.
It's like this constant subtle hum that permeates the quantum world, preventing anything from ever truly being at rest.
That's a wonderful analogy. It underscores how dynamic and lively this microscopic realm truly is, even in conditions that we traditionally associate with stillness.
Hmm.
Zero-point energy is a fundamental aspect of quantum mechanics and has far-reaching implications for numerous physical and chemical phenomena.
This is all so fascinating, but I have to ask, how do scientists actually go about calculating this elusive zero-point energy? It seems like a rather tricky concept to pin down and measure.
It's certainly a challenge, but thankfully we have sophisticated computational techniques at our disposal. These methods involve solving the Schrödinger equation, a mathematical framework that describes the behavior of quantum systems.
So it's like creating a mathematical simulation of the quantum world, allowing us to explore its intricacies from a theoretical perspective.
Exactly. And by analyzing the results of these simulations, we can estimate the zero-point energy of various molecules and systems.
It's incredible to think that we can use math to probe the deepest secrets of the universe, even at the subatomic level.
Indeed. The more we learn about zero-point energy, the more we unravel the fundamental nature of reality itself. This exploration into the realm of hydrogen bonds and the quantum mechanics governing their behavior has been incredibly enlightening.
I completely agree. It's amazing to think that something so small can have such profound implications for the world around us, shaping everything from the properties of water to the functioning of enzymes.
It's a testament to the interconnectedness of the universe, how phenomena at the tiniest scales can ripple outward, influencing the macroscopic world we experience.
Before we move on, I'm curious to hear from you, our listeners. What are some of the insights that have resonated with you during our discussion so far? Has anything sparked your curiosity?
We're always eager to hear your thoughts and perspectives. Feel free to share your comments and questions below.
Absolutely. Engaging with our audience is one of the rewarding aspects of this journey of exploration.
Who knows, maybe your questions will inspire new avenues of scientific inquiry and lead us to even more profound discoveries.
The beauty of science lies in its constant evolution, always seeking new knowledge and understanding. So keep those curious minds engaged as we venture further into the intricacies of hydrogen bonds.
We'll reconvene in our next segment, where we'll explore how these quantum principles manifest in the real world, shaping the properties of familiar substances and driving essential life processes. We've spent quite a bit of time delving into the quantum mechanics behind hydrogen bonds. But now let's zoom out and see how these principles play out in the tangible world you experience every day.
Yes, let's bring this back to reality. It's one thing to talk about wave functions and tunneling, but I'm eager to see how these abstract concepts translate into something I can actually observe.
Well, think about water for a moment, that seemingly simple substance we all rely on. It's a perfect example of how quantum phenomena at the microscopic level give rise to macroscopic properties we're all familiar with.
Okay, I'm all ears. What's so special about water from a quantum perspective? Aside from the proton tunneling dance parties we discussed earlier, of course.
Think about the properties of water that make it so essential for life. It has an unusually high boiling point for such a small molecule. It's an incredibly versatile solvent capable of dissolving a vast array of substances, and it exhibits high surface tension, allowing those fascinating insects to stride across ponds.
You're right, those are all essential properties and we often take them for granted.
Exactly. And all of these remarkable characteristics stem directly from the ability of water molecules to form those intricate networks of hydrogen bonds we've been discussing.
So those tiny quantum interactions between protons and electrons are ultimately responsible for shaping the macroscopic behavior of water. That's incredible.
Precisely. It's a beautiful illustration of how the quantum world, often perceived as abstract and esoteric, directly influences the tangible reality we interact with every day.
It makes you wonder what other hidden quantum wonders are shaping the world around us. But let's not forget that hydrogen bonds aren't just limited to water. They play a crucial role in a myriad of other scenarios, many of which are vital to life as we know it.
Absolutely. Consider DNA, the blueprint of life itself. The double helix structure of this remarkable molecule is stabilized by a network of hydrogen bonds between the base pairs, ensuring the faithful transmission of genetic information across generations.
So those tiny quantum bonds are holding the very secrets of heredity together. That's mind-blowing. What other molecular marvels rely on this quantum dance?
Let's not forget proteins, the workhorses of our cells. These complex molecules responsible for countless biological processes owe their intricate three-dimensional structures to, you guessed it, hydrogen bonds. These bonds help fold the long chains of amino acids into specific shapes, dictating their function.
Wow. So from the very essence of life to the intricate machinery that keeps us going, it all boils down to these tiny quantum interactions. It's a whole new way of looking at the world.
Isn't it fascinating? It truly underscores how quantum mechanics, often relegated to the realm of theoretical physics, is deeply intertwined with the very fabric of our existence.
I have to admit, I'm leaving this conversation with a profound sense of awe, a newfound appreciation for the hidden quantum wonders that shape our reality.
That's the beauty of scientific exploration, constantly revealing the interconnectedness of the universe and challenging us to expand our perspectives.
Well, I think we've covered an incredible amount of ground in this exploration of hydrogen bonds, from the mind-bending realm of quantum mechanics to their tangible impact on the world around us.
We've only just scratched the surface, but hopefully we've sparked your curiosity and inspired you to delve deeper into the mysteries of the universe.
To our listeners, we hope you've enjoyed this journey as much as we have. If this discussion has ignited any questions or insights, we encourage you to share them in the comments below.
We're always thrilled to engage with our audience and explore these fascinating topics together. Who knows? Maybe your questions will spark new avenues of scientific inquiry, leading to even more profound discoveries.
The world of science is vast and ever-evolving, and there's always something new to learn and uncover. So keep those curious minds engaged, and we'll see you next time for another adventure in the realm of science.
Until then, keep exploring, keep questioning, and never lose your sense of wonder.
Thank you for listening to Podcast Learn and Fun. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.